this today's, I'm your lecturer for today's meeting, and we're gonna be discussing the paper E sample problems. So let's proceed with the problems. A quadrilateral has sides 5, 6, 7, and x, such that the side x is opposite the side of length 5. If x is an integer, how many values of can x take? So, does anybody have an answer? Okay, so it seems like someone answered D. Is there any other answers? Okay, then I'll present the solution. So, firstly, I, for um these types of geometry problems, you usually want to construct a diagram. So, since we know the side x is opposite the side of length 5, we must have something like um, this, wherein the side of length x is opposite the side of length 5. Now, sorry, when presented with a problem like this, where you want to find how many values can um an a variable take, it's, you usually should think about the triangle inequality, because it's very common to appear, and also like it helps, it restricts the quantities of x. So firstly, what do we know from let's say this triangle. Let's call it ABCD actually, so that we don't get lost. What do we know from triangle ABC and ADC? What basically, in other words, how can we restrict X using the triangle inequality? Actually, I forgot to mention the triangle inequality is that for a triangle, for another triangle ABC, actually let's call it DEF. For another triangle DEF, when you have side lengths A, B, and C, it's that A plus B is greater than or equal to C. Actually, for a non-degenerate triangle, it's usually just A plus B is greater than C. B plus C greater than A, and A plus C greater than B. So how can we use this information to restrict the values that X can take? Find the possible values. Yeah, actually, you're right. We can find the possible values of A. So, and that in turn restricts X, which is CD, because we can use a triangle inequality to bound X. So in that case, um, we know that 11, which is 5 plus 6, in this case, is greater than AC. The reason why I didn't put the greater than or equal to sign is because we know this triangle and this figure is quadrilateral. And we usually don't like include degenerate quadrilaterals. I mean quadrilaterals with degenerate triangles because they don't look like quadrilaterals. So yeah. Anyways, for we also look at it's, it's we also look at triangle ACD wherein we know that 7 plus x is greater than AC. Now this doesn't look like much information, but remember, ABC and ACD aren't the only triangles. So we also have ABD and BCD in order to apply the triangle inequality. So in this case, we must have five. We must have 5 plus 7 is greater than BD. This and also BC plus CD, which is 6 plus x, is also greater than BD. So um now that we have all this information, how can we use it? Well, yeah. I mean, elimination could work, but I don't think it really does work because there's inequalities all around. So it kind of makes things a bit messy. I think we should go back to Cobalt's suggestion here. Find the possible values of AC. I mean, since we know that AC is less than since we know that AC is less than 11, um, we have a finite number of values of AC we can test. So let's just look at all these values of AC. Firstly, we can't have AC equals zero, of course, because we don't want the degenerate triangle in there. So let's look at AC equals one. We don't want to do 11 cases. I'm just gonna try to show how we can approach this more systematically. If AC is equal to one, then 7 plus x is greater than one. So x is greater than -6. That doesn't tell us a lot, but it also shows like, oh, if AC um if AC is um less than or equal to 7, then we basically just know that x must be positive. I must be just only needs to be positive. It can be take on values from one or greater. Anyways, so since it doesn't imply any more restrictions on x, um, we have to look at BD instead. So in this equation here, because this equation doesn't tell us that much yet, um, we know that 6 plus x is greater than BD, right? Well, thus, um, we must have um. Oh yeah, sorry. I also forgot to mention. We also know that Oh wait, yeah. Um. The sum of these three legs must be greater than or equal to x because if you can think about it like you want to stretch the three legs as much as possible. So to stretch them the most means to just put them all in a straight line, which is just adding them up. So we also have what 18 um it's less is greater than x. Anyways, besides that, just from seeing this, we just from seeing this, we have um this doesn't actually need to tell us this. I'm sorry. This only this equation only tells us that BD is greater than BD is less than 12, right? But this also means that if BD is less than if BD is less than or equal to 6, then we again can let x equal anything. And actually, with these two conditions alone, AC is equal to 1 and BD is greater than equal to 6. Actually, not even AC is equal to 1, but let's just put this and let's put a speed is equal to 6 or something, we can um we realize that this doesn't put any more restrictions on x. X can just continue to be a positive. It can be any positive integer between 1 and 17, and so how much and so x can just take any positive integer from 1 to 17, which means the answer is 17. Sorry, but yeah. Does anyone get it? Does anyone not get it? Or does anyone have any questions? Okay, and I'll move on to the next problem. It's like, anyways, um, given problem two, given that 1434 ba- base x written in base x is equal to 100,001 base 3, find x. Does anybody have an answer to this problem? B. Okay, that's a very interesting answer. Um, well, actually, you're right. It is B. But why? Oh yeah, I haven't. There's also another reply thread in the chat. That's like, did anyone find the answer already? It was. Oh yeah, it was about the second problem. Um, yeah, yes, you can use trial and error, but there is a systematic way on solving it, and it usually is much more consistent. So in that case, I'll show you the solution using the systematic solution. Okay, but yes, it is 5. So here, let's try to convert one. But let's try to convert 1434 base x into something we can actually handle. Like, so the definition of base is like, um this is the ones place for um this is the ones place. This digit is in the ones place. This digit is in the tens place, or basically it has value equal to x. This digit, which is 4, has it's in the hundreds place, which is equal to x squared. And this is the thousands place, which has where each not each digit in the that place has a value equal to x cubed. You can think about it. You, you can think about like the normal base 10 system similarly to this. So, for example, 737, right? It's just a random number. So, um, this is the one space, right? This is a 10 space, or each digit in this place has value equal to 10. And similarly for 7, each digit here in this place has value equal to 100. So you can think about it as 7 times 100 plus 10 times plus 3 times 10 plus 7 times 1, or 737. So we can convert 1434 base x into some um polynomial in terms of x. In this case, we have 1 times x cubed plus 4 times x squared plus 3 times x. Sorry for my weird writing. And then plus 4 times 1, which is just 4. And this we can just repeat the same process for 100,001 base 2 equal to, well, this is the one space, 10 space, 100 space. Actually, it's the ninth space, technically, we call it. But either way, it's 27, 81, and 243, right? So this is equal to 243, which is the 100,000th place for base 3 numbers instead, plus 1, or 244. Now, we can simplify this a bit. We can move all the terms into the left-hand side, and we can just ignore the multiplication. We can just um put them into coefficients. So x instead we have x cubed plus 4x squared plus 3x, and then this is just 244. So if you subtract 244 from both sides, you get um plus 3x minus 240 equal to 0. Now, um okay, actually it is preferable to do this by trial and error because x is an integer, positive integer. But you can also oh um you can also read that like you can bound this expression. So since all these terms must be um positive because x is positive because it's the base of a number, we must have x cubed is less than this number 240. So we must have x must be at least 5. X must be at most 5, at most 6. Sorry. So we can try all values from 1 to 6, and this number 240 seems large. So let's try 6 first. So it's x cubed, which is 216. Wait, sorry, no, it's 16. Yes, 216 plus 4 times 36, which is 144, plus 3 times 6, which is 18. Now this value is too large. We already know this because 216 plus 144 is already greater than 240. So we're going to try 5 instead, x equals 5 instead. And in fact, this seems to work because 145 plus 4 times 25, which is 100, and then plus 15 is equal to 240. So in fact, it works. And since it satisfies this equation, this then implies that x is equal to 5. And you can plug in directly to this to see that it works. So x is equal to 5. Does anybody have any questions? Oh, okay. All right. Um, in that case, I'll be moving on to the next problem. Now, I will directly admit I I'm not so familiar with this question, but we can use we don't we can use the choice multiple choices, the the multiple choice structure to figure it out, which is actually really necessary for competition sometimes. Also, side note here, this problem is actually wrong because um if the conic passes through the point one comma one, then this equation is like this is an integer, but this is not an integer because it's 7 squared over 5. So I'm I'm not gonna skip this, but just take note that this question there's no right answer to it. But anyways, um if you see here, all of these equations are of the circle formula x minus h squared plus y minus k squared is equal to r squared, right? This is the formula for a circle. But the thing is, okay, for a circle, the directrix is technically at infinity, right? But it has a directrix given by a line, which doesn't make any sense here. So it can't be any of these options. And so our only choice left is the option that isn't a circle, which is supposed to be D. How you do traditionally. That's the part I'm struggling to figure out. But what what I was thinking was that since the since the conic section has a single directrix, since it says a directrix, we know um it's a parabola, right? But the line isn't like y is equal to blank. So we also know it's a rotated parabola. And so we have to find some way, which is usually done through complex numbers, but to rotate the parabola given the direction. Sorry, the parabola is actually like something like this. The direction is something like this. But anyway, that's what we're supposed to do. Wait, my apologies. And either way, it's supposed to be something like this, I believe. And so we have to like rotate the parabola somehow to get just a regular parabola with a directrix and the focus. But anyways, that's how I would have probably done it. Again, I'm sorry, I'm not. Yeah, but this the answer is wrong here. Anyways, we're moving on to number 4. If anyone, by the way, if anyone has a solution for this, I would actually like you can comment here if you want to. I would actually like to know. Anyways, problem 4. Let f of x equals sine of 2026x and g of x equals x over 2026. How many times do the graphs y equals f of x and y equals g of x intersect for 0 less than or equal to x is less than or equal to 5? Sorry for my. Anyways, does anybody have an answer? Okay, people are saying, why is that? I mean, there's a answer really close to it, 4051 here. Why isn't it 4051? And similarly, why isn't it answer C and D? I mean, there's a 2026 in both. Uh, okay, in that case, I'll give a solution now. So, firstly, again, given these types of problems where you really don't know where to start. Oh, yeah, Cobalt, you're, yeah, you're right, actually. But, yeah, you're right, actually. But um, there's also some points that are closer to one. So, how do you deal with those? That's the question. Well, either way, given a question like this where you don't know where to start, it's usually better to graph it. In fact, it kind of gives you a hint here. How many times do the graph? So in those types of questions, it's usually helpful to graph it. And since we're given a purely positive, I'm purely non-negative, sorry, domain, I'm just going to show the right hand side. Okay. So let's just try to first visualize how would sine of 2026 x look like. It's going to oscillate really fast. So I'm just going to try to emulate it as closely as possible. So it's going to be something like this. Sorry. It has a it will oscillate constantly up and down. Right? Well, that's cool, but how do you actually try to interpret this? Well, what g of x equals to x over 2026 is also just a line. So I'm sorry, it's just a line. So something like this. Of course, so there's gonna be a lot more points in this because these values are kind of a lot less um massive compared to the graphs where I'm to the equation we're given. In that case though, we can try to give an indicator of sorts of how many values I'm sorry. We can try to get an indicator or make an indicator and so that we can um group each intersection point into um constant. I mean, we can group the each intersect in each pair of intersection points. Basically saying um we want to group these in such a way such that we can count the number of intersection points more easily. So let's just try let's try Cobalt's suggestion actually. So since we can see here that every time the graphs intersect, it's always bef- each they intersect twice, always before um goes to zero, kind of. But it kind of like the indicator is side of x is going down and it intersects zero. That's when you know that there are two values, two intersection points preceding it, excluding the next indicator in a way. So we also have to take into account the starting and ending conditions because those are usually where it gets messed up a bit. But let's just try to like count the number of ways until that ending point. Where in that ending point is around it's 2026 because that's when g of x becomes greater than 1, which is outside the range of sine of 2026x. So um in that case um we need to see in what direction sine of 2026x is going just right before it hits g of x. Basically, what we mean is like what is the module? What is the when we take mod 2 pi, which is kind of a very abstract term, but it sort of works in a way. Um, what in what quadrant will sine of 2026 x be in the unit circle? That will help us determine if it's going up or down, which will help us assess whether um it's 4,000 whether sorry, I'm trying to find the right word. Um whether it um whether the whether the indicator continues to work or is there another point outside what the indicator basically a point after not before any indicator. So in that case we'll be looking at actually but for now we're going to be looking at the values of the indicators here. I'm sorry for using that word so much. um First point notice here is the first time it's the second time it hits zero. So that is basically equivalent to um x is equal to well sine of x hits zero around here. So and since this period is 2 pi over 2026, we know that it hits zero for the second time at pi over 2026. And then sorry, I'm not gonna put it. It hits it again at um well you're going it's the fourth time it hits. So it's 3 pi over 2026. And similarly we can keep going until the last indicator for x is equal to 1. But purely based on the but pi is kind of irrational, so it's not really I mean let's just try to look for some let's just try to go to the other part first. But in that case, since it only comes in pairs of two, we also know the answer can't be 2026 squared minus 1 or 2026 squared because um there are only at least 2026 times 2 pairs because um x there are only about there are only at least 2026 indicators. So you can see here. Sorry, I'm getting the I mi- but anyways, in that case then you have to look at their final indication here and their oh yeah, sorry. Actually wait no. Since X is greater than oh sorry. But we're given a domain here less than zero. I mean close to zero, sorry. I mean yeah. So wait, sorry. Cobalt's actually right, sorry. But not like yeah. Um since x over 2026 is very close to zero, then 2 pi over 2026 is also very close to zero. So we actually don't really we actually know that the last time they um intersect is only is only due to the rate it's only due to the domain given, not because g of x becomes greater than one. I'm sorry. Therefore, um you only need to count here. And notice the last time it goes um it the last time it's still less than 2 pi is at the 4051 over 2026. 4051 pi over 2026. By the way here, um notice there the indicator points I'm defining here are all the odd are all those with an odd coefficient of for pi here, besides the 2026. Either way though, we can count how many indicator points we have, which are 2026. And so there are at least 4052 points because since there are 2026 indicators and there's always 2 points before the indicator, before the previous indicator, sorry for all the lingo, um, there must be at least 4052 points. But now, how do we know that there aren't any more points besides that? Well, um, oh, this is 4050. If you multiply this by 4050 by 2026 to plug it to f of x, um, you get the sign of a non-even multiple pi, which implies it's going down. And since it's going down from the negatives, as each indicator point means that the that f of x equal to zero, it won't intersect again until the next indicator, until it touches until it touches zero, wherein it'll be 2 pi. Therefore, there are exactly 4052 intersection points. Again, it's kind of hard to see, and I'm sorry for the bad wording, but like the general idea here is to um locate points. I mean, to define points on the graph. On one of the graphs, usually the one with like the sign of x or something, that always has a constant amount of points that you want before the next intersection point. The next um indication point. Basically, in this example here, for example, there are always 2 points, two intersection points before an indicator point. So since we know there are at least 2026 indicator points, there are at least 4,052 intersection points. But then we realized that from looking at just the last part of it, that since side effects is going down, we know that it won't intersect another time. Is that clear? I'm sorry for the explanation. Again, it's kind of a hard concept to think about, but whenever x is even, it's negative. Um, wait, what do you mean? Like, oh, whenever x is um between an okay, f of x. Wait, no, it's actually when x is even pi. When x is exactly even pi, that is positive. If x is odd pi over 2026, we're basically saying 2026 pi. Sorry, 2026x is an odd multiple of pi. Then we know it's negative. So basically, it's the other way around. Basically, from 4051 pi over 2026, which is the last indicator point we make use, to 2 pi, it went around like this. So it never went above zero. So that means it couldn't have possibly um touched an intersection, another point, a point from x over 2026. Either way, though, I'm going to proceed to the next problem because I think we're running out of time. If positive integers x comma y exists such that log of 4x plus 2 log of y is equal to 5, then find the sum of the least and greatest possible values of log of y. I'm sorry, does anybody have an answer to this? Okay. In that case, I'll explain the solution. So firstly, um, since you have the addition of logs, and since you're given in general, it's usually nice to use the log addition and the multiplication formulas. So here we know that log of 4x. I'm sorry. We know the we know that log of m plus log of n equal to log of mn. Um, if you, I can show the proof actually. Where basically, if you take 10 raised to both sides, get 10 to the, you can use the fact that 10 to the m plus n is equal to 10 to the m times 10 to the n. Sorry. And since this is 10 to the log of m, you get m, and then since it's a 10 to the log of n, you get n. So you have m times n is equal to mn, which is true. So you basically prove this identity right here. But either way, This is true. And you also have um log of mx equal to m. Sorry, log of x plus m log of m. These two identities, I think, will be helpful here. Also, if you want to know, also we're doing this in log base 10, basically saying if 10 to the x is equal to y, then um x is equal to log of y. It's basically the inverse of raising something of inverse of using the base to raise something to a power. I don't know if I worded that correctly, but that's basically how I think of it. Anyways, um, we use this identity here. Sorry. Sorry, that was something. Anyways, log of. Oh yeah, we also forgot something. If you have m log of x, then that's the same as saying log of x to the m. In fact, all of these three identities can be proved just by raising both sides to the 10th power. So yeah, that's basically it. Either way, though, we want to use this identity first. Let's move to this side. So we have log squared of y, which is just log of y times log of y. Sorry, log of log squared of y plus 4 log x. I'm sorry, plus log of 4x equals 5. And then we, ha- we can combine these together. Log of 4x times log squared of y equal to 5. Or basically 4x times log squared of y equal to 10 to the 5th. Now, you want log y, right? Um, yeah. I mean, wait, no, actually, it's log of log squared of y. I'm sorry, log of 4x times log squared of y. Because you move this to the, you move this here. You move the power. You move the multiple. Basically, the logarithm terms multiplication outside uh, into exponentiation inside. But that was a good attempt. Anyways, here we want to find the possible values of log squared of y. So let's just isolate log of y for a bit. Okay, I'm sorry, log of y. Um, but square rooting kind of seems a bit messy here. So I'm just gonna keep it log squared of y for now. So this, in other words, this must be. I'm sorry. This equal to 10 to the fifth over 4x, or is equal to 10. I'm sorry, 5 to the fifth times 2 cubed over x, right? Well, um, in that case, since x is a positive integer and the log of y cannot be a, an integer, cannot be a rational number unless, I'm sorry, if you plug in a positive integer here, then log of y cannot be a rational number unless log of y is an integer. We can actually prove this by realizing that log of, sorry, basically in other words, if log of x if log of x is equal to a rational number where x is an integer, then for um then m over n is an integer because 10 x is equal to 10 to raise to the m over n, and we know that this cannot be this whole thing cannot be an integer unless it is a multiple of 10. Was that right? Yeah. So basically saying this is a positive. Is this is an integer. Either way though, um what we have here is that this must be a positive integer. And more so, since this is log squared of y, this also must be a perfect square. So we just need to find the greatest and least possible values of x because they're they're inversely proportional. Log y and x are inversely proportional, such that the 5 raised to the 5 over 2 cubed and times 2 cubed over x is a perfect square. Which basically means we can either have 5 we can have 5 raised to 5 times 2 cubes equal to x, or log squared of y is equal to 1, which is log of y is equal to 1. In other words, y is equal to 1. I mean, y equals to 10, sorry. Or um, x is the smallest value possible, which is 2 times, I mean, sorry, 2 times 5, which is 10. Where we're in 5 to the 4 times 2 squared to log squared of 5. I'm sorry, log y is equal to 1. We don't care about y actually. I mean, we can use y, but it's going to be really large. So we just need log y here. Either way though, log squared of y is equal to 0.5 to the 4 times 2 squared. By the way, we got this value just because we want this to be even, this exponent to be even, and we want this exponent to be even. So we to make this the largest even number less than the exponent. So we choose 2 to the 1 and 5 to the 1. Either way, we have log of y equal to 5 squared times 2, which is 50. And so we have these two values, right? We just need to find the sum, which is 51. And I think that is the answer. Let me check. Yeah, you're right. Yeah. The answer is 51. Does anybody have any questions? Okay. In that case, I'll move on to the next question. Find the largest prime divisor of the number 2 raised to the 24 plus 3 raised to the 12 minus 2 times 3 to the 6 times 2 raised to the 12. Does anybody have an answer? Uh, okay. In that case, I will be sharing the answer. So here, um, since we can recognize this actually as the difference of squares formula because this is something squared plus this is something squared minus the square root two times the square root of these. Basically saying um if we want to find the largest prime divisor of something, we usually look at patterns somewhere. And actually, in general, we want to look for patterns everywhere. And we have this pattern here. So this is just the difference, not the difference of two squares. The square of the difference of two numbers. Sorry for not making that clear. So this is just, since this is just 2 reasons 12 squared, mine plus 3 to the 6 squared, my handwriting's bad, minus 2 times 3 to the 6 times 2 to the 12. We can just take these as our numbers, 2 to 12 and 3 to the 6. And since this is minus 2 times their product, we must have 2 to the 12 times 3 to the, minus 3 to the 6 squared. That must be our expression. Yeah, perfect square trinomial, basically. And realize this can be factored a lot. So this is something squared, right? So 2 raised to the 12 minus 3 to the 6. First, we can realize this is the difference of squares, right? Which is 2 to the 6 minus 3 cubed times 2 to the 6 plus 2 to the 6 plus 3 cubed. In fact, these values are already computable, but let's try. I'm going to try making these a little lower. Okay, so um we can use then the difference of cubes here and the sum of cubes here, where 2 squared and 3 are these. So we have 2 squared minus 3 times 2 squared plus 3 plus 2 times 3, which is 6 plus 2 squared. And plus, oh, sorry, no, sorry. I forgot to square this. 2 to the 4 plus 2 squared times 3, which is 6, plus 3 squared, which is 9. Wait, no, sorry, not 6. 12 plus 9 times, um, now we have the factorization for the sum of cubes, which is 2 squared plus 3 times 2 to the 4 minus 12 plus 9. Now we can compute these expressions here. This is 1. This is 16 plus 12 plus 9, which is 28 plus 9, which is 37. Anyway, it looks like we have a nice prime number here. 2 squared plus 3, which is 7. And 2 to the 4th minus 12 plus 9. We have all this squared, but I'm going to move this actually. Times 60, which is basically saying this is 16 minus 12 plus 9, which is 13. Now we clearly have the a prime number here. And since this is squared, it doesn't change the prime divisors and the largest prime divisor. So because they're just squared. So since we know 37 is the prime number, um And it's the largest prime number out of here. This must be our answer, 37. If I am right, yeah, this. Does anybody have any questions? My apologies. Okay. In that case, I will um be doing moving on to the next problem. So problem number 7. A Penchick has 10 fish in front of him. He can either swallow a fish, whole, or peck at it. However, he cannot swallow 2 fish in a row. How many ways can he eat all 10 fish? So does anybody have an answer? Yeah, okay, guys. I mean, maybe it is a big number, but this is a really tight condition, kind of. Because there or at least there are at maximum 2 ways and 10 ways, right? Because he can either swallow a fish whole or peck at it. And those are the only two choices he can do, right? In order to eat the 10 fish. So since there are only two choices at maximum for each choice, there are at maximum 2 ways and 10 choices, which is 1024. So the answer isn't as big as um maybe what you would have thought. So nice to consider that so that it helps you see if your answer is definitely wrong or maybe not wrong. Maybe. I feel like it's counted. That's true, but there still seems to be a lot of ways. And I mean, yeah, you can actually probably casebook it. Maybe. But there is a better approach. No, it does not include cases. There is a cleaner way. Okay. I'll let you guys think for a bit more. Okay, I'm back. Um, yeah, actually, Gerald, you actually got it. Oh, sorry, Gerald. Is it Gerald or Gerald? Either way, yeah, it is 144. Um, stars and bars. mm, but but the thing is, okay, let's call a swallow an S. Let's call a swallow S, right? Sorry for my pattern. Okay? And a peck when pen when the penchick pecks, let's just call it P, right? So each term for it, basically let's call it the first fish. Let's make this the first fish that he chooses to do something to, the second fish, etc. The fish he eats before, um, I'm sorry, the fish he eats now depends on the fish he ate before, which is not like stars and bars because the stars and bars you only have to count the their each variable is independent. It's just that each variable is independent of each other. You just need to find like ah, but yeah. The thing is though, like the arrangement is two arrangements. I mean, it's harder to count directly in the case, but still though can't um use stars and bars for this. Like the okay, blah, blah. I will reveal the solution. So yeah, actually it's the Fibonacci sequence. But why is it the Fibonacci sequence? Well, we can use recurrences for this to answer this. What is a recurrence? Well, it's just something that depends on the previous terms, right? So let's just try to handle this. Um, let's just try to build a recurrence for this. So since the since the next fish effects only depends on the previous fish effect, let's actually let's divide this into cases. Even though there's no actual casework, but there is some case dividing. Actually, yeah, you're right. Um, Cheryl, more that I think about it, it's kind of casework, but yeah. So let's say you have like some sequence here, right? Something, something, something. Let's say you end with a with the Penchick swallowing, right? Something. What must the next term be then if the Penchick just swallowed a fish? Can it be S or P or both or none? Yeah, it has to be a P. Why? Because he cannot swallow two fish in a row, right? So in order for this to not be another sorry, I put a P. This is a better be a P. In order for the Penchick to not swallow twice, this must be a P. And let's say this is a totally acceptable sequence, right? Um, this of picks and swallows and X. Um, for every sequence that ends with S, we must have a P right after it. And in fact, if you remove the S here, this since the swallow doesn't make any other does since without the swallow um you don't have any other conditions. So these is just the number of regular sequences that you want. So basically saying if you have um n amount of terms and a to the n and a sub n is the number of possible ways you can eat all n fish, then this is just a to the n minus a sub n minus two. How do we know? Because again, wait, actually, wait, I'm not sorry. I'm thinking. Um, sorry, wait. If it ends with an S, then it's this must be a P, right? So it's actually a to the n minus three. Sorry, if a small is before it, it'll actually I'm as small as after it that it's actually a condition before it. Right? But since it ends must end with it, this third term before I term before the S must be a P, and there's no conditions for a pack. It actually must be a to the n minus three, a sub n minus three. But this is just one part of a sub n, right? What is the um thing that the Penchick did before now before the current fish was a peck? Okay, in that case, then it could be anything. So it can be either a P or an S. So this is just basically two times because you have. I'm sorry. Wait. Yeah, two times. Since you have a P and S, the number of ways. Wait, actually, it's not Fibonacci, is it? Wait, it might be Fibonacci. Wait, but anyways, it's two times number of ways to basically um if, if you have a to the n, if you have n fish here, then this is 8 n minus 1, right? This whole thing, this is just a to the n minus 1 waves. And you have two ways for the next choosing. So in other words, a sub n is just equal to a sub n minus 3 and 2. You can do it any order, but um 2 times a sub n minus 1 plus a sub n minus 3. If I did that right, I'm not sure actually. But we know that we can do a recurrence from this, where since a sub n is the number of ways you can eat all n fish, right? Um, for the first fish, he has two ways. The Penchick has two ways to do so, and similarly for two fish, for two fish, it has a um. Well, it cannot have SS, which is swallow times swallow and another swallow. So it's two squared minus one, which is three. And then a sub three, let's just compute for a sub three again. And for the last time, because since we can continue, we can do the not a recurrence starting from a sub four. So in this case, then try to find a sub 3, which is not that hard. You just need to watch out for all the for the possible type of SS. So there are 8 ways minus. Let's do complementary complement. So there are 8 choices, and then you have to subtract the number of cases with SS, which is two, which are 3 ways from SSP, PSS, and SSS. So yeah, 2, 3, 5, and then A sub 4 does must be 2 times 5, which is 10, plus 8 n minus 2, which is 12, which is 2, so it's 12. And then A sub 5 is equal to 2 times this, which is 24. Did I do this right? Sorry. I'm sorry. Did I do this right? I might have not. Um, oh yeah. But it is a recurrence. I just did it wrong. Um, oh, sorry. This is n minus 2, a to the n minus 2, because this is guaranteed to be a p. So this can be an S or a p, but this is guaranteed to be a p. And this right here is a to the n minus 2. So yeah. My apologies. A to the 1 is still equal to 8 to the 2 is equal to 3. 8 sub 3 is equal to 5. But anyways, either way though, a sub n is equal to 2 times a sub n minus 2. So it's a sub n minus 3. Which means that um yeah, you're right. Jero, you're right. A to the 4 is equal to 2 times 8 sub 2, which is 6, plus a 1, which is means that a to the 4 is equal to 8. And similarly, 8 to the 5 is equal to 2 times 8 sub 3, which is 10, plus a sub 2, which is 13, which means it's 13. A sub 6 is equal to. This is the Fibonacci sequence, but it's just a slightly different form of it. So A sub 4, A sub 7 is equal to 2 times this 26 plus 8, which is 34, and then we can continue from this. You can see that these two are equivalent just by realizing that you can plug into the Fibonacci sequence. They're not the same, exact same though, but because you need a sub 1, a sub 2, and a sub 3 to get it, but still it's very similar and equivalent in nature. You have the 2 terms. Either way though, you have, yeah, basically it's equivalent in nature because you can plug in a to the n minus 1 from this, wherein wherein you can plug n minus 1 here. So you have a to the n minus 1 is equal to a to the n minus 2 plus a to the n minus 3, right? Basically, this is the Fibonacci sequence. So you can plug in this into a to the n minus 1, and you get the same thing as this. In that case, though, um, a to the 9 is equal to 89, and lastly, A sub 10 is equal to 144. And that's how you get A sub 10. Or, yeah, you're right though. Either way though, um, the number of ways is the Fibonacci sequence. Um, does anybody have any questions? Yeah, yeah. But it's really nice actually. Recurrences are really nice. If you look at, if you like know how to do them, because like they apply to a lot of combinatorics problems. That's what makes them so nice. They're kind of like casework, but less bashy, but still as useful when you're stuck. But either way, um, the, I don't think we still have some announcements before we end. Unlike last time, there is no lecture. There is no JPOMO pre-lecture after this. So, but we s- but take note that the JPOMO qualifying stage um is on is 3 days from now on May 9th, 2026. Also, the recording of this lecture will be posted shortly on my YouTube channel, and also like um for those joining JPOMO, please read the content primer. Um, yeah. I can repeat it. Even um, this I think you can stop recording. Actually, if you want, you can continue. But either way, okay. So how you get formula is basically, let's say let's define a sub n as the number of ways to eat can to eat n fish given the conditions, right? But either way, sorry, I was talking about. Um, in that case, um, let's try to find let's try to define a sub n in terms of a sub n minus one or a sub n minus two or etc. Where so let's um and since the fish that he eats now depends on the fish that I'm the way he eats the fish now depends on the way he eats the fish before, but it only depends on the fish only it only depends on the fish he ate directly before. Um we must we can separate this into two cases basically. One where the last fish he ate he swallowed it, which means this is n minus one terms, and the way where the way he ate the last fish was a peck. Okay, in both cases, there are n minus one terms, n minus one fish he ate before it, and then you have to find a new way, the way number of ways to eat the fish now. So in the case where he swallowed before, he cannot swallow now. So there's only one way he could possibly do it, which is a peck, right? And since these two terms are already specified, um, and this term must also be specified, also must be defined because it's right before a swallow, in which there cannot be two swallows. we only have this left, which is n minus three terms. So that that are free for a sequence to be for normal any number of ways to get n minus three pages to be made. Which because basically saying um in this case um if he swallows he before the fish um eats now it's equivalent to the number of eight ways to eat n minus three fish because the last three terms already predefined and the term before and term before this last p here can be can be any s or p, which means um it leaves the n minus three terms free basically. So there are n minus three sequences in this case. A to the n minus three sequence. A sub n minus three. In this case, sorry for the bad wording. Either way though, now in this case here, this is already defined, but this can be either S or P. This next term can either be S or P. And for the term below it, it can be any sequence because the P doesn't have a. If you pack, there doesn't need to be any condition before it. So this is just A to the n minus two. But we also have to account for the two choices of S and P. So there are two times A sub n minus two. So since we already used all cases, we have A sub n is equal to 2 times A sub n minus 2 plus A sub n minus 3, right? And so we only have to compute A sub 1, A sub 2, and A sub 3, right? In order to find the values of A sub 4, A sub 5, just purely by substituting. And so we do that exactly. Yeah. Basically we add A sub n minus 3. So A sub 1 is equal to 2, A sub 2 is equal to 3, basically saying the number of ways to eat one fish is two, the number of ways to eat two fish is three because there are four choices in total for the two choices of the fish. And then you subtract the S cases. And then A sub 3 is equal to 5. You can do this with case work. And then A sub 4 is equal to, then we must substitute A sub 2 and A sub 1 into this. Which means this is equal to um 2 times A sub n minus 2, which is 2 times A sub 2, which is 6 plus 2 is equal to 8. And similarly, for A sub 5, you can do the same thing, where it's 2 times 5 plus 3, which is 13. And this follows the Fibonacci sequence, actually, because um they are fundamentally identical. Yeah, you can check. Well, basically, for these types of problems, um, if you really like have no way to like do it without casework, it's usually nice to consider a recurrence or trying to find a recurrence in general. And it's also usually like a big hint when you have like a, when you have um a condition that depends on the previous or two previous or previous two or previous any number of choices. So basically saying um if the problem asks if the problem states that the sequence depends on previous values of itself, then which is called a recurrence, then it's usually nice to try to make a recurrence using casework. Um, Another way these are your values. You can check. Um, but the stars and bars work. Actually, wait, you're right. Stars and bars could work. It's just that you have to pieces from 1 to 5, k+1 to k+5. It's not that hard, but it's a bit tedious. This is also a bit tedious, but like it's more consistent. So it's usually the better way. But you can try. Actually, I can show you. I think I can show you the stars and bars way. So this is not seven. But let um we're gonna let S be the separator here. Okay, and there has to be a non-zero amount of peace between the S's. Um, or else you get a coefficient of Russell. In that case, though, there has to be two variables that are not zero. But let's take into account later. So there are 10 fish, right? So in that case, you have to consider from one swallow to five swallows, right? But either way, you must have a. Let's just do let's just work through the cases first. Let's try the first one where there's no S, right? They just there's just one. I mean, this is obvious already. It's one. And then you must find the next case where there's one S, right? Well, realize there are two groups now, and both of them can be can be zero. So it's just basically saying finding all, and there are nine stars or p's to distribute among the two bars. So a plus b is equal to 8, or basically saying um there are 8 plus 2 minus 1 choose 2 minus 1, or in other words 9 choose 1 ways or 9 ways. I think yeah, it works. And similarly, but okay, actually not similar here. But now you have another case here, right? There are two S's. Now instead, this P has the amount of P's between the two S's here, of course, must not be zero. It's okay. I'm gonna explain it for those who you know for just to find the intuition. So um, this must be this can be zero. This can be zero. So that's the regular stars and bars condition. But then for B, this cannot be zero. So you're essentially taking one star to add to this thing, to this group right here, so that it can always be positive. In other words, it's A plus C plus B or A plus B plus C is equal to, well, there are 8 stars, but you're using one star to make this positive. So it's equal to 7, right? So you have 7 plus 3 minus 1, choose 3 minus 1. Wait a second. Okay, right. So it's 9 choose 2. Actually, you may notice a pattern here. So it's 9 choose 1 plus 9 choose 2. Sorry, 9 choose 0 plus 9 choose 1 plus 9 choose 2 plus 9 choose 3, all until. Wait, is this right? I'm sorry. I might have made a mistake here. 5. Oh, sorry. This is 9. No, it's not 9. Wait, sorry. Yeah, 9. 9 plus 2 minus 1. 10. Sorry, it's 10. Wait. Yeah, sorry, it's 10. Wait, sorry. So it's actually 10 choose 1. But the pattern is still kind of folded. 1 plus 10 choose 1 plus 9 choose 2 plus 8 choose 3 and etc. until um 6 choose 5, right? Now, I think, yeah, I think you can just compute this directly. So you have 11 plus 9 choose 2, which is 36, plus 8 choose 3, which is 56, plus 7 choose 4, which is 7 choose 3, which is 35, and then and then you have 6 choose 5, which is 6. Yeah. Sorry. Sorry. Anyways, you have this, right? So you can group this. Um, so it's 11 35 plus 36, which is 35 plus 35 plus 1. Sorry. These are just subtle things that make it a bit faster. So you have 77 for 36 plus 35 plus 6. And then you have plus 11, so that makes it 88. And then plus 56. And this is just 144. So yeah, there are 2 ways to do it. Yeah, stars and bars. It's a sum of stars and bars basically. But either way, that's how you do the problem numbers. Let's All right. Does anybody have any questions about other problems besides problem number 3? Because I'm not fully sure if I can do it. Like, I mean, it's gonna take me a while to solve it. But yeah, I'm being honest here. Uh, okay. In that case, I think we're done now. Um, thank you everyone for coming to the meeting. I think if anybody doesn't have any more questions, we can end it.